The last fundamental theorem that we're going to learn about is the divergence theorem. And before I state it, I just want to remind you of the general form of all of these fundamental theorems. So any kind of fundamental theorem of calculus looks like the following. On the one hand, we're computing an integral over some region of the derivative of something. And exactly what that region is and exactly what the derivative is depends on the situation, but we'll always have some kind of integral that looks like this. And on the other side of the equation, we always have the integral over the boundary of the region of the thing. The fundamental theorem of calculus looks this way, the fundamental theorem of conservative vector fields looks this way, Green's theorem and Stokes' theorem both look this way, and the divergence theorem will look this way as well. The kind of region that we'll be interested in with the divergence theorem is a three-dimensional region in R3. So you should think of a solid filled-in blob, maybe something like this. So this filled-in blob I'll call E. And on the left-hand side of the divergence theorem, we have an integral over E. Well, since E is a three-dimensional region, the kind of integral that we'll be computing is a triple integral. And then in the integrand, surprise, is the divergence of a vector field. So in this theorem, the D smiley face is the divergence of a vector field F. The divergence operator is acting like the derivative. And that's the left-hand side of the theorem. Remember that the divergence of a vector field is just a scalar valued function. It spits out a number. So this expression here is just a regular triple integral. And the theorem says that this triple integral, the triple integral of the divergence, equals, well, on the right-hand side, we'll be integrating over the boundary of this region. So if I have a three-dimensional blob, what is the boundary of that region going to be? It's going to be a surface. You should think about the boundary of a three-dimensional region as being the shell. So that tells us that the kind of integral that we have on the right-hand side is a surface integral. If I remove the derivative sign from the vector field, I'm left with just the surface integral of the vector field over the boundary. Now, anytime we talk about a vector surface integral, which is what this thing is, we have to talk about an orientation of the thing that we're integrating over. So for the divergence theorem, the statement holds when the boundary surface is outwardly oriented. So on my picture here, I could draw an outward pointing normal vector on the boundary surface. This is what we'll always mean by the boundary of some three-dimensional region. The convention is that the orientation is outward. And there we go, that's the divergence theorem. I'll say it again, the triple integral of the divergence of f is the surface integral of f over the boundary surface. Said a little differently, the triple integral of the divergence is the flux through the boundary surface. That's what we're computing on the right-hand side. And as with Green's theorem, with Stokes' theorem, with all of these fundamental theorems, the divergence theorem can be useful in both ways. It depends on the situation. Sometimes you might be interested in computing the flux through some surface, and the divergence theorem will tell you maybe it's easier to compute the triple integral. Or conversely, sometimes maybe you'll be interested in a triple integral, and the divergence theorem will make it easier to compute via a surface integral. So it's a two-way road. Before we look at some examples, I just want to make a quick remark to relate this back to Green's theorem. I think since Green's theorem is a low-dimensional theorem and it's a little easier to visualize and get your hands on, and it's something that we're used to at this point, contextualizing all of these other theorems like the divergence theorem and Stokes' theorem in terms of Green's theorem is helpful, at least for me. So to remind you what Green's theorem says, it says that the double integral of the curl of a vector field in 2 dimensions over some region D in the plane, this is equal to the line integral of the vector field along the boundary curve. So the picture here is that we have some 2-dimensional blob, and on the left-hand side, we're computing the double integral of the curl. So inside here, I have all these microscopic circulations representing the curl. And the left-hand side of Green's theorem is adding all of these up. And like I talked about in the Green's theorem video, what this says is that when you add up all these microscopic circulations, you get the macroscopic circulation around the boundary curve. And to rewrite the right-hand side a little bit, the vector line integral of f over the curve, by definition, is just the scalar line integral of f dot the tangent vector. Right? If you think about how we compute a vector line integral, we utilize the tangent vector of the boundary curve. So in my picture, this would look kind of like this. Now, what I actually want to do is I want to relate the divergence theorem to the flux version of Green's theorem. I haven't talked about this in a video yet, but you may have seen the flux version of Green's theorem somewhere else. And to get the flux version of Green's theorem, what we do is instead of computing the vector line integral over the boundary, in other words, instead of computing the circulation of the vector field around the boundary, we compute the flux through the boundary curve. How do we do that? Instead of dotting with the tangent vectors along the boundary, we rotate those tangent vectors 90 degrees to the right and consider the normal vectors. So if you recall back when we talked about flux through a curve, this is how we computed it. And in the flux version of Green's theorem, on the left-hand side, we're not computing the integral of the curl. The flux version has you compute the integral of the divergence of the vector field. So, to say this again, the flux version of Green's theorem says that the double integral of the divergence of the vector field gives you the flux of the vector field through the boundary curve. Think about this and think about what we just talked about with the divergence theorem. This is exactly what the divergence theorem says, just down a dimension. In the divergence theorem, we have a 3-dimensional region, and on the one hand, we're computing the integral of the divergence over that 3-dimensional region. And the theorem says that this is the same thing as computing the flux through the boundary. That's exactly what the flux version of Green's theorem says. We've got an integral of the divergence over the region, and that gives us the flux through the boundary. Anyway, I think this is kind of nice. I talked about this with Stokes' theorem, and it's the same case with the divergence theorem. You can think about Green's theorem as 2-dimensional projections, in some sense, of Stokes and the divergence theorem. Anyway, let's do some examples. As usual in these videos, the first example I'm going to do is going to be a relatively straightforward application of the divergence theorem, and then in the second example, we'll do something a little more fun. But for this first one, here's what we're given. We're given a vector field, x squared, arctangent of z cubed, and yz. And we're given a surface S, which is the outwardly oriented boundary surface of some region. And that region is the one contained by the surfaces z equals 0, x plus z equals 1, and x equals y squared. The goal of the problem is to compute the flux of this vector field through this surface S. Now, before I start talking about some ideas, let me draw a picture so that we have something slightly nicer to look at besides my handwriting. We have a couple surfaces here that are cutting out some region. One of those is z equals 0. That's the xy plane. I won't draw anything for that. One of the other surfaces is x equals y squared. In the xy plane, that would look like this. And then in my head, the surface I'm visualizing is this shape going up and down forever with no restriction. But I'm not going to draw that yet, just because I don't want to muddle the picture. So for now, I'll just draw the trace in the xy plane. Now the other surface is x plus z equals 1, which in the xz plane, this would be a line. When x is 0, z is 1, and then when z is 0, x is 1, so the line would look like this. And then I know that the surface is the plane, which contains this line. It has no variation in the y direction, so it would extend forever like this. And since we're being cut out by x equals y squared, the kind of shape that we would get is something like this. This looks like a wedge of cheese. And we're also told that this is outwardly oriented, so I'll just draw on a little normal vector like this. Okay, so I'm going to sound like a broken record at this point, but it's still an important concept, which is keep in mind that we're in the middle of a video about the divergence theorem. So that's probably what we're going to do. But I have said nothing about the divergence theorem in the statement of this problem, so if you come across this in real life, it's up to you to make that decision. And to reiterate, the goal of the problem is to just compute the flux of f through s. So ultimately, we just want to compute some surface integral of the vector field through the surface. One option you always have is to compute this directly. So if we entertain that thought for a second, I don't know, maybe we could do it, but it'd be a little annoying because this surface, this boundary surface, has 3 smooth pieces. So you'd have to parameterize 3 different chunks and break this into 3 different integrals. That itself would be annoying. But even if we were to do that, this arctangent of z cubed thing, that looks scary. And in general, it feels like something that I would not be able to integrate directly. So that's a red flag to me that we might want to do something different. And, the other obvious indication here that the divergence theorem might be useful is the fact that we're told that this surface we care about is the boundary surface to some 3-dimensional region. By definition, this is what the divergence theorem is for. So both of these things indicate to me that the divergence theorem is going to be a good idea rather than computing this directly. So let's apply the divergence theorem and see what happens. In order to do that, we need some 3-dimensional region. So in my solution, I'll be explicit about that. I'll say, let E be the region enclosed by this surface S. And this is where the outward orientation is important. Since S is outwardly oriented, this means exactly that S is the oriented boundary of E. Remember that when I stated the divergence theorem, I said that when we talk about a 3-dimensional region and its boundary, we take the orientation to be outward. And that's exactly what we have here. So this statement pretty much just means that we can apply the divergence theorem directly. So I'll do that. By the divergence theorem, the surface integral of f over s, this is the thing we ultimately care about. Well, S is the boundary of E, so by the divergence theorem, this is equal to the triple integral over E of the divergence of F. And the idea here is that maybe this triple integral is going to be easier to compute. So if I compute the divergence, I'll take the x derivative of the x component of the vector field. That would give me 2x, plus the y derivative of the y component. Well, arctangent of z cubed is constant with respect to y, so the derivative there is 0. So I can already tell that this is going to be a lot easier because I've completely killed off this arctangent mess. And then the z derivative of the z component is going to be y. So now at the end of the day, we just have a triple integral over this 3-dimensional region of 2x plus y. And that's the divergence theorem. From here on out, we're just in the world of triple integrals. We don't have to worry about what this means or where it came from. We're just evaluating a triple integral. I've talked about this before, but I think it's really important to keep this in mind as an organizational thing when you're doing these problems. You can think about the divergence theorem as being a bridge from the world of surface integrals to the world of triple integrals. That's all it is. So once you apply the theorem, you've walked across the bridge, and now you're completely in the world of triple integrals, and you do whatever you need to do over there. So now we travel back in time and think about, how would I evaluate a triple integral over this region? Well, if I think about setting up the bounds of an iterated integral, it seems like doing z first is probably the easiest thing. The region's definitely z simple. If I fix an xy value, the lower bound is given by the xy plane, so that's z equals 0. And then when I move up, the thing I run into is this plane. I hit the x plus z equals 1 plane, so that defines my upper bound. If I solve for z, this means that the upper bound is going to be 1 minus x. So that will be my innermost integral. And then I take the region and squash it into the xy plane. This will give us a two-dimensional region, and this will define the remaining layer of bounds. So if I look at that region, it seems like doing x next would be best. For a fixed y value, x is going to vary like this. This means that the lower bound is going to be y squared, and the upper bound will be this line, which is x equals 1. When I drew the region, I talked about how this plane hits the xy plane when x equals 1. So our x integral will go from y squared to 1. And then to get the y bounds, I project again. So at this point, I just have to find the intersection points here and here. Those are at -1 and 1. So there's our outermost integral with respect to y. And then we evaluate it. So most of this is just basic calculus. I'll let you watch. And eventually we get down to an integral with respect to y from -1 to 1 of a bunch of powers of y. And it's kind of annoying, but I can use odd symmetry on some of these. Any of the odd powers of y are going to integrate to 0 because the interval -1 to 1 is symmetric across y equals 0. So this one, this one, this one, and this one, the integrals of all these terms are going to be 0. So that leaves me with 1 minus 2/3 is 1/3, and then a minus y to the 4th, and then a plus 2/3 y to the 6th. And this one I just integrated in my head, which means this final answer that I got may or may not be correct. If you really care, you can check me on it. But as usual, the important part of a solution like this, I would say, is this first part, where you recognize to use the divergence theorem, which is the new concept that's being tested here. Anyway, this is a pretty straightforward application of the divergence theorem. In this last example, we're given a vector field f, but we're not actually told what the vector field is. The only thing we're told is that it's defined on R3 and it has divergence 2. Then we're told that S is the unit sphere with outward orientation, and T is the boundary of the cube -2 to 2 cubed. So this is the cube centered at the origin where each side has length 4, and this also has outward orientation. Finally, we're told that the surface integral of f over s over the sphere is 3, and the goal of the question is to figure out what the integral over the cube is. Let me start out by drawing some pictures. drawing the actual three-dimensional picture is going to be a little hard, so I'm going to draw two pictures, and one of them will be a side view. But first, we have this sphere. It has outward orientation, so I'll draw an arrow like this. And then we have this cube. And I won't draw this precisely, and this cube looks way too big, but there's some bigger cube enclosing the sphere, and it also has outward orientation. Now, just to make things easier to think about, like I said, I'm going to also draw a side view, which you can think of as some sort of central cross section. This red circle would represent the sphere, and this blue square represents the cube. Okay, so we have some pictures. Now we have to think about what to do. Our ultimate goal is the surface integral of f over t. And there's one thing that we definitely cannot do. We definitely cannot evaluate this directly. We don't even know what f is. Even if we parameterized the boundary faces of the cube, which we could definitely do, it's not going to help because we don't know what the vector field is. So clearly we have to do something clever. And what I'm going to do is I'm going to use the divergence theorem to relate the integral over t to the integral over s. Since we already know what the integral over s is, somehow we want to use that information to get the integral over t. The natural way to do that is to fill in the region between the cube and the sphere. That's the region that I'll apply the divergence theorem to. So I'll give this a name. I'll say let E be the three-dimensional region inside T and outside of S. So inside the cube, outside the sphere. In my two-dimensional picture, that would look like this region. And then I won't try to color this in the three-dimensional picture just because I would color in everything and it wouldn't be insightful. But you want to think about the three-dimensional region between the sphere and the cube. Now, the most important part here is to make sure that we get the orientation of the boundary correct. This is the main reason I wanted to do this example. We know that when we apply the divergence theorem, the boundary of the region E is going to be outwardly oriented. For us, the boundary of E is going to consist of two separate pieces. It'll consist of the blue piece and the red piece. If we think about T, T is definitely outwardly oriented. So part of the boundary will just be T. But if you look at the red circle, which again represents the red sphere, the normal vector for S is pointing in to the purple region. So when we say outward, I don't mean globally outward, like pointing off to infinity. I mean out of the region. You want to think of outward as being away from the region. So the normal vector for S is pointing in the wrong direction because it's pointing in to the purple region. So what this tells us is that the boundary of E is plus T minus S. Think about that for a few seconds to make sure it makes sense. So now by the divergence theorem, we can say that the triple integral over E, over this purple region, of the divergence of f is going to be the surface integral of f over the boundary of E. Well, one of the things that we're told in the problem is that the divergence is 2. And then above, we figured out that the boundary of E is t minus s. And what's the point? On the left-hand side, if I factor out the 2, I'm left with the triple integral of 1 over E. That just gives the volume of E. So the left-hand side is going to be 2 times whatever the volume of E is. And then on the right-hand side, I can split up the surface integral into 2 different ones, an integral over T minus an integral over S. The The point is that we already know the integral over s, and we're trying to figure out the integral over t. Now on the left, the volume of E, we don't have to do calculus to figure this out. It's comprised of a cube and a sphere. So to get the volume, we could take the volume of the box, take the volume of the whole cube. Each side has length 4, so this would be 4 times 4 times 4. And then subtract out the volume of the ball inside. Well, that's a ball with radius 1. So the volume of that is going to be 4/3 pi times 1 cubed. And then on the right-hand side, we have the integral over t minus, well, we're told that the integral over s is 3. And it looks kind of disgusting, but that's an algebraic equation that we can just solve to get the integral over t. Move the 3 to the other side and do some simplification, and we're done. At the end of the day, the integral of f over t is 131 minus 8 pi over 3. That was kind of fun. And this kind of thing should feel familiar. We've done similar problems with Green's theorem and Stokes' theorem. So here you can think about the divergence theorem as a way to relate integrals over different boundary pieces. This was the general strategy of this problem.